Good morning. I hope that you all are having a fantastic day. Today we are going to be talking about conic sections. Conic sections are literally just sections that you get by cutting through a cone in one shape or another. So you can cut through a cone to make a parabola, an ellipse, a hyperbola. You can also cut it just laterally to make a circle, which is the conic section you all are most familiar with. So in this video, what I'm going to do is just quickly go through each of the conic sections and their basic formats and how each of them works. The one that you're most familiar with is a circle. Its base form is just x minus h squared plus y minus k squared equals the radius squared. So if I'm looking at a circle that looks like this, I know that it's centered at the point 4, -1. So if I were to try to graph this thing, I'd have a point that's at 4, -1, and that would be the center. Then, because this value is 49, my radius is 7, so I'd be going 7 to the right, which would put me at 11, -1. 7 up, which would put me at 4, 6. 7 to the left, which would put me at -3, -1. And at 4, -8. So I would have a circle that goes around the origin looking like this, and that's straightforward enough. It's not a very good circle, but you get the idea of what's going on. Now, our other conic sections are a little bit more complicated. I'm actually going to start by talking about the ellipse and the hyperbola, and then I'm going to move to, the ellipse and the hyperbola, and then I'm going to move to the parabola last, because the parabola is sort of weird, even though it's one you guys are used to dealing with. So first, let's talk about an ellipse. An ellipse is sort of an elongated circle. It's going to be a circle that's been stretched out either vertically or horizontally, or it can be on a slant, though we're not going to get into that in this class. On the sheet that I gave you guys, if you're looking for how an ellipse gets laid out, it can either have a major vertical axis or a major horizontal axis. If it has a major vertical axis, that means that it's taller than it is wide. If it has a major horizontal axis, that means that it is wider than it is tall. You notice that they have x in front in both of these. It doesn't have to be, this is addition. But the difference is that a vertical has the a underneath the y term, and a horizontal has the a underneath the x term. And this a value is going to always be the bigger value in the case of a ellipse. So they give you a bunch of things about center, vertices, foci, major axis equation, minor axis equation, the equation that relates a, b, and c, which is a squared equals b squared plus c squared. Notice that this is different than c squared equals a squared plus b squared, which is the case in a hyperbola. But I think that it's probably easiest to go through this just looking at an actual equation and walking through how an equation would work. So this third equation that I have in my paper is the equation of an ellipse. It has two terms. They are being added together. The fact that they're being added together and that both are being squared tells me that it is an ellipse. Because the term underneath the y is larger than the term underneath the x, I know that this is going to be a vertical ellipse, which means that it's going to be taller than it is wide. If I were to try to graph this, sorry, I have a dog that's eating in the room with me right now, so if you're hearing munching, that's what's going on right now. If we were try to graph this ellipse, first of all, I think that people would generally recognize that there's a vertex at the point 1, 3. So I'd go 1 right and 3 up. And there's my center. Now, I should say center, not vertex. Because this number is larger than this number, I'm going to use this number to find what are called the vertices. Because these are underneath the vertical value, I'm going to go 3 up and 3 down, because in my equation, it's represented by a squared from this point. So I will move 3 up and 3 down. And those 2 points will be what are called my vertices in my ellipse. This 4 means that I'm going to move 2 right and 2 left. So I have a point here and a point here, and those are called my covertices. My covertices are on a shorter axis than my vertices are because my vertices are always going to be further away from the center than the covertices. I end up with an ellipse that looks like this thing, which is a total of 6 units tall and 4 units wide. In this situation, a squared is equal to b squared plus c squared. And you might ask, well, what in the heck is c anyway? C is where I'm going to find what are called the foci of the ellipse. The foci are going to be somewhere around here. The foci in an ellipse are actually representative of a point from which the sum of the two distances to any point on an edge from the foci is going to be the same no matter where you go. So this distance is equal to this distance is equal to this distance, and that's what the foci are there for. The foci are really what make this thing into an ellipse, and that's where C comes into play. You won't have to worry that much about it right now in this class, but that's what that language is referring to. If I wanted to find out what C was, I could take a squared minus b squared to get c squared, and that would mean that 9 minus 4 is equal to 5, so c equals the square root of 5. So I would be going the square root of 5 up and the square root of 5 down from the vertex because it is a vertical ellipse rather than a horizontal ellipse. That's the basics of dealing with an ellipse, and now we're going to talk about a hyperbola, which is almost the same equation, except that instead of an addition sign, we have a subtraction sign. Whereas an ellipse has values that are coming together, a hyperbola has values that are moving apart from one another. You're going to go through the same basic process for finding out where the center is and where the vertices and covertices are. So I would have a point in this case that's at 3, -1. So I have a point that's at 1, 2, 3, -1. That's going to be my center. I'm going to go 2 to the right and 2 to the left because these are my terms that are underneath x. So I go 2 right and 2 left, and I go 3 up and 3 down. Now, a hyperbola is a little bit different from an ellipse because in a hyperbola, I don't figure out whether it's vertical or horizontal based on which of these values is bigger. In a hyperbola, I figure out whether it's going to be vertical or horizontal based on which of these two values is positive. So in this case, the x term is positive, which means that this is going to be a horizontal hyperbola. And a horizontal hyperbola is going to open left and right rather than up and down. Now, a hyperbola is going to have some more stuff going on in it. It has asymptotes in it. And those asymptotes are created actually by this little box that I drew, just sort of connecting all of my vertices and covertices. This is a vertex, and this is a vertex. And these 2 points are covertices because they are on the opposite axis to the direction that this thing is opening in. If I connect that box, I end up getting the ability to draw these diagonal lines. And these diagonal lines are going to create my asymptotes. My hyperbola is going to open horizontally towards the asymptotes. And it's going to open in that direction, and it's going to open in that direction. If this term had been in front and the positive term, and this term had been the negative term, my graph setup would be exactly the same. The only difference would be that now I'd be opening this way and I'd be opening this way. Once I can find the foci of my hyperbola, it's going to be the points that these are going to be curving around. And in this case, in a hyperbola, c squared is going to be equal to a squared plus b squared. So if I take 9 plus 4, I get 13. So the square root of 13 is in between 3 and 4. So if I go 3.5-ish, I would have a point there and a point that's out here. And those are my foci. Those are going to be the points that the hyperbola curls around. So that gives me my ellipse, which is an elongated circle, and my hyperbola, which is sort of a circle that's opening outward, or an ellipse that's opening outward. And you can remember that it's opening outward because of this minus sign. The last equation that we have to deal with is probably the trickiest one, because it's unlike all the rest of them. It is that of a parabola. Now, if you'll notice in this case, this is a parabola that we're not used to seeing. It has the y term getting squared rather than the x term getting squared. We're still going to go about finding our vertex of our parabola in the same way that we did before. So if we're trying to graph this, I'll rewrite my equation down here. So I have y minus 1 squared equals 12 multiplied by x minus 1. So if I'm graphing this thing, as you would expect, I'm going to have a point that's at 1, 1, and that's going to be my vertex. That's based off of the 1 for the vertical and 1 for the horizontal. Now, the tricky bit is understanding which way you're opening. This 12 is going to be the key to what we're doing here. Now, this 12 in our equation is actually equal to 4 multiplied by p. So in our equation, 4p is equal to 12. And that means that p is equal to 3. That 3 is going to allow us to find out where the focus is. Now, in this case, this is a horizontal parabola because the y is getting squared. If you think about it, when we have like y equals x squared plus 2, that's a vertical parabola because the x is getting squared. In this case, it's a horizontal parabola. So the focus is going to be 3 units to the right of the vertex. There's my focus. And then I can use the focus to create something called the latus rectum. The latus rectum is going to go through the focus, and it is going to be a line that this thing curves through, and it's going to have a length of 4p, which means that it's going to be 12 units long. Well, that means that it's going to go 6 up, and it's going to go 6 down. So if I've gone 6 up and 6 down, my parabola curls around the focus, looking like that, and that's my parabola. I have a horizontal parabola because the y is getting squared. If this had been negative 12, I would have been opening in the leftward direction, and p would have been negative 3. That would tell me that I'm going in this direction instead. This is a lot of information to throw at you all right now. I only ask you to do a few problems on each of the conic sections. This is going to be one where you're going to really need to look at the notes that I sent out, in addition to paying attention to this video and coming to office hours. So I hope that that clears up some stuff and gives you at least a few examples to work off of, and I look forward to hearing your questions. Have a wonderful day, and I will talk to you all again soon. Bye.